Hi Year 11, it's Mrs. V here, and today we are going to be talking about ionic structure and bonding. So let's get started. For this lesson you're going to need your structure and bonding booklet, so if you haven't downloaded that, please do so. We're going to be looking at page 22. You probably need a pen or pencil. You might want to jot down a few notes as we go through. Let's get on it. Okay, so some of this stuff you've already learned in year 9 and 10. We've done a lot of work on ionic compounds. We just didn't really call them ionic compounds. So you know that they're made up of positive and negative ions. You've been doing that since year 9. You started talking about how the atoms could gain or lose electrons to make ions, and how those ions got together in compounds in the right ratio that the overall charge was 0. That's how we actually worked out how to get the formula for an ionic compound, is we made sure we had the right number of positives and negatives, that all of the opposite charges cancelled out and the overall charge was 0. There are simple ions or monatomic ions. Monatomic, of course, just means one atom, and they're formed when atoms gain or lose electrons, and that's usually to obtain an octet in the outer shell. If you're talking about hydrogen and helium, though, that's a duet, okay, because obviously there's only 2 electrons in that first shell, so they can't get 8 electrons. There are polyatomic ions, which are groups of atoms that are bonded together, and the overall ion has a positive or a negative charge. Normally the atoms are held together by covalent bonds, which we're going to learn about in around about a week's time, and the overall molecule has extra electrons or not enough electrons for all of the atoms that are in it, and overall that gives it a positive or a negative charge. Positive ions are called cations, negative ions are called anions. They are terms that I'm going to expect you to be using. It's up to you how you work out how to remember that. I always remember cations are positive because there's a big plus sign sitting in the middle of that word. But I have had students in the past go, well, cats are a really positive thing, or in fact they said positive. I know, how good is that? And they said anions were negative because onions made them feel negative. But it's up to you how you go about remembering that. All right, so ionic compounds. Where are we? Progress. No, it's not going to progress. Okay, now it's going to progress. Okay, naming ions. Right, metal ions just have the same name as the metal. So sodium makes the sodium ion, rubidium makes the rubidium ion, magnesium makes the magnesium ion, and so on and so forth. There are some metals that can have variable valences. That's the transition metals, or the D block elements. In fact, some of them are in the bottom of the P block as well. But we have a Roman numeral that tells us what the valence is. So when we name those, we include a Roman numeral. So if we're looking at iron, it can make the iron 2 ion, or the iron 2 ion, or the iron 3 ion. Lead can make lead 2 or lead 4. In fact, many of the transition metals can have, 6 or 7 different valences. Monatomic non-metal ions. That means just the non-metals by themselves. They have names that end in "ide", I-D-E, and we put that "ide" ending on the non-metal name, but we kind of chop the end off of the non-metal name. So oxygen makes the oxide ion, nitrogen the nitride, sulfur the sulfide, bromine the bromide, etc., etc., etc. Polyatomic ions, they have endings that are either "ate" or "ite", and that tends to be the ones that include oxygen, and the ones that end in "ate" have more oxygen than the ones that end in "ite". So sulfate is SO4 2-, sulfite is SO3 2-. And next year we'll learn that the "ate" or the "ite" are actually referring to oxidation states, but that's something for next year. Remember the 2 notable exceptions that you need to know. Well, the one you have to know is the hydroxide ion. It's polyatomic, and it contains oxygen, but it ends in "ide." What fun would it be if there were no exceptions to the rules? Cyanide is your other one. All right, here's the bad news. We're not going to give you a table of polyatomic ions on your data sheet anymore. I expect you to know the formulae of the ones that are on the screen. Anything that's not on the screen we'll still give to you, but I expect you to know the ones on the screen. Oh, come on, guys, it's 7 things that you have to learn. Do some memory work. So you need to know name, charge, and formula of all of those ions. It's only 7. You can do it. I believe in you. Moving on with today's lesson then. So that all that stuff before you knew. It wouldn't be proper to continue without our learning intentions. They're still with us, and we've got 2 of them today for you. You are going to learn to distinguish between the terms structure and bonding, and you are going to learn to describe the structure and the bonding of ionic compounds. As we go through this topic, you'll be describing the structure and bonding of all the different types of compounds, but for today, just ionic. You will know that you have achieved your learning intention if you can describe the structure and the bonding in an ionic compound. So what do these terms mean, structure and bonding? Structure just tells you the way that the atoms are arranged in a substance. So whether it's in a single unit like a molecule, or whether it's in this massive continuous 3-dimensional lattice, they are structures, just the arrangement of the atoms. Bonding, however, tells you about the forces that are holding the atoms in that particular arrangement. So bonding is forces, structure is an arrangement. When we talk about bonds, there are some bonds that are really strong, and we call them the primary forces. Ionic bonds, covalent bonds, and metallic bonds are the primary forces, and we're going to learn about those this term. There are, however, some weaker chemical bonds, and things like the bonds that exist between molecules, and they're called the secondary forces. We're going to learn about those next semester. I know you're excited. I'm excited too, but we must wait. So ionic structure. If you're asked to describe the structure of an ionic compound, what do you say? Well, first of all, that they form crystalline lattices. A lattice is a continuous 3-dimensional arrangement. And you can see in the picture there, that is a depiction of sodium chloride. The sodiums are the purple ones and the chlorides are the green ones. And you can see that they exist in this continuous 3-dimensional structure. And we always have the ratio of positive and negative ions in the lattice so that the overall charge is 0. So if that means that when we write the formula NaCl, we're not meaning 1 sodium and 1 chlorine. We're talking about the fact that the ratio of sodium to chlorine is 1:1. And if we go through the whole lattice and count up all the sodiums and count up all the chlorines, there'll be the same number of each. So the ions form this structure to get, it's a really low energy arrangement. Another way we can say low energy is stable. So it's really stable arrangement. And all stuff is really lazy. All matter is lazy. It wants to be in its lowest possible energy form. And the way that the ions can do that is to make sure that there's a lot of attraction between them and not much repulsion. So we try to get we know for charges, opposites attract and like charges repel. So we try to get the opposite charges as close as possible, and we try to get the like charges as far away from each other as possible. And that's going to be the most stable arrangement that we can have. And that causes a specific arrangement normally where all the positives are surrounded by negatives and all the negatives are surrounded by positives. And that particular shaped particle is called a crystal lattice. And the extra stability or the reduction in energy that the ions get from forming that lattice structure is known as lattice energy, because in chemistry, we call it what it is. We don't have to make up fancy terms. The energy associated with getting into a lattice is called lattice energy. So different ways can they do that? Well, there's 7 basic arrangements, and they're called the 7 primitive crystal systems. The only one we're going to deal with is the first one, the cubic lattice. We are going to assume that every single ionic compound we study has a cubic lattice structure. It's not the truth, but do you really want to study 7 different systems and all the variations of those 7 different systems? I don't think so. So just for simplicity, we're going to concentrate on cubic lattices. And for that reason, we're going to tend to use examples where we have a 1-to-1 mole ratio of the positive and the negative ions, because they are the types of substances that produce cubic lattices. So everything's going to be a cubic lattice for all of our discussions. But it's worth noting that there are actually other types. So I don't want to try and pull the wool over your eyes and tell you that the only type of lattice in existence is a cubic lattice. It's not. It's just the simplest kind, and that's the one we're going to focus on. That's pretty much all I wanted to say about structure. So let's move on to bonding. Oh, except we're going to talk about the way that we actually see diagrams of the lattices. And this one is a 3-dimensional depiction of the sodium chloride lattice. It tries to show how the atoms are all arranged in 3 dimensions on a 2-dimensional surface. And so we draw these little boxes to represent the 3 dimensions. This one is a cross section. So if we want to show the lattice, it looks like it's 2-dimensional. It's not. You've got to imagine that that lattice continues out in front of the page and behind the page as well in 3 dimensions. But to show the cross section, it is usually enough for us to discuss properties. This one, the blue ones are the positive ions, the sodium ions, and the grey ones are the negative ions, the chloride ions. And you can see this one shows that the sodium ions are smaller than the chloride ions. They are. They actually are smaller. What I want you to think about before the next video is why you think that would be the case. So get your periodic table out, have a look. I think you're going to be able to work it out. This is the simplest kind of diagram that you're going to see of a crystal lattice. It doesn't actually show different sizes. It just shows circles for the ions. And in fact, quite often we don't even show the formula. Quite often we just write plus, minus, plus, minus, plus, minus through the lattice. So normally when we're talking about properties, we'll be looking at this much more simplified diagram. Now I think it's time to move on with bonding. There we go. So ionic bonding, this is going to tell us what's holding those ions in their lattice positions. Why do they stay in that lattice position? And this is due to the forces of attraction, which are known as electrostatic attraction. Electrostatic attractions are just attractions between charges. So attractions are between opposite charges, and like charges repel. But in that ionic lattice, there's a really strong attraction between the positive and the negative ions, and that's what holds the whole lattice together. All right, I'm going to stop sharing the PowerPoint, and we're going to go on and talk about the crystal lattice a bit further and the ionic bond further on a PowerPoint. I'll get rid of that and then share another screen, that one. And fingers crossed that I get it right, because I recorded this video the first time and didn't get this right. So fingers crossed that you can see my diagram of sodium chloride in 3 dimensions now. This is the lattice, and this is the representation to try and show the lattice in 3 dimensions. So the red ones are the sodiums and the green ones are the chlorides. Just going to pick on this particular sodium. And we're going to talk about why that sodium stays in its place. So you can see that above and below, there are chloride ions. And this is a sodium ion. Now, the chloride ion above is attracting the sodium ion, and the chloride ion below is attracting the sodium ion. And if you have a look at this week's extras, you'll find a video in there that you could watch on Coulomb's law, and which talks to you about the strength of attraction between charges depending on the size of the charge and the distance between them. So because the chloride above and below the sodium has the same charge, and they are equal distances, they very much equally attract. There's also a chloride ion on this side and a chloride ion on that side. And they are both attracting the sodium ion absolutely equally. There's also a chloride ion in front and a chloride ion back there below the sodium ion. So it's getting equally attracted on all sides. And I like to think of a little ball bearing. And I'm going to draw a magnet here and a magnet there, and they're the same strength magnet, and a magnet here. We're just going to do this in 2 dimensions. So all of these are magnets of the same strength. And we're going to put the ball bearing right in the center so it's equally distant from all of the magnets. My drawing is pretty hopeless and therefore I haven't shown that. But you can imagine if I have this arrangement that this ball bearing is going to be attracted to that magnet. What's going to stop it from moving toward that magnet? Well, it's actually equally attracted by that magnet. And so it's kind of in this approach avoidance conflict. It wants to be attracted to both the magnets, but it's being pulled equally in opposite directions, so it just can't go anywhere. And this is exactly the same situation here and here, where that ball bearing is equally attracted to both of those magnets. So it can't get closer to either of them because there's always the other magnet pulling it in the other direction. And if you imagine that we had a magnet out in front of the screen and behind the screen, then we would also have that equal attraction. So what actually happens then is your forces are totally balanced on the little ball bearing here. And so the ball bearing just stays in place. So over here in the lattice, that's the situation you have. You have that equal attraction in all directions. And so the forces on this sodium in the middle are absolutely balanced, and therefore the sodium just stays there. These sticks that are shown here, they don't actually exist. They're just forces. They're not actually physical things. So what's holding those ions there is just those forces of attraction for all of the ions around it. And that makes the ion stay exactly in place. The ion will still vibrate. The atoms still vibrate in a solid lattice, but it can't actually move towards any of the chloride ions because there's always one on the other side pulling it back. And whenever I think about this model, I think about when I worked at Dixon College, and we had this cool toy in the staff room. And this cool toy was a magnet so this was a magnet. And then we had a steel globe. And what you could do was you could actually suspend that steel globe at exactly the right distance that the force of attraction for the magnet exactly balanced the weight of the globe. And therefore it would just stay hovering. Of course, whenever students came to visit us in the staff room, the first thing they would do would be tap on the bottom of it to make the ball fly up and stick on the magnet. And then we'd have to go through that frustrating process of balancing those forces again. However, because we were science teachers and a little bit nerdy, we quite enjoyed that. So whenever I think about the ions in a lattice being held, hovering in between all their oppositely charged ions, I think of that toy where you get that perfect balance between the forces, and therefore you can just have that globe hovering in the air. And this is made use of. This picture over here is a maglev train. I don't know if you've heard of maglev trains. maglev stands for magnetic levitation. And they actually, the train hovers above the track by magnetic attraction and repulsion, and it's actually driven along by attraction and repulsion of magnets as well. So very cool, the maglev train. Anyhow, that's all I wanted to talk to you about today. So I will see you in the next video, and study hard. Bye.